I'm glad to be here to introduce our new storage engine, SMRSTORE. SMRSTORE is a joint work of OSS and Feng team at Alibaba Cloud. Object storage service is for persisting or retrieving objects such as pictures. OSS has exabyte level data on CMR drives in production. SMR seems to be a good opportunity to reduce the cost. By overlap checks, SMR drives can provide 25% higher density than CMR drives, and therefore they have better cost efficiency. I'm sorry. However, SMR drives divide the address into fixed size zones and only support sequential write within zones. And some SMR drives also have a limit on the open zone count because of the backward incompatibility and limitation. SMR drive is not a drop-in replacement for a CMR drive. Our goal is to improve cost efficiency of OSS by replacing CMR drives with HM-SMR drives without compromising on performance. Here is a big picture of OSS architecture. OSS front-end layer preprocesses user requests and forwards them to the service layer. The service layer has two major functionalities. The first one is to write objects to Feng files, and the other one is to maintain the mappings from object names to locations within Feng files. OSS uses Pangu file system as a persistent layer. Pangu master manages the metadata of Pangu files, and Pangu Chang server is responsible for data persistence. Chang server starts an ext4-based storage engine for each CMR drive, and each chunk corresponds to a file in ext4. Let's learn some semantics of Pangu file and chunk. Pangu file is append-only, like HDFS, and divided into multiple chunks. Chunks is also append-only, and only the last chunk is writable. When creating a Pangu file, users can control the max chunk size by setting a limit. When chunk size reaches the limit, Pangu will seal the chunk and allocate a new one for write. In some cases, chunk size can also be variable. For example, if Pangu file is small or write failure is encountered, chunks could also be small. So when adopting SMR drives, we do not expect to change the semantics of Pangu file and chunk. So the key is to implement our existing chunk store interfaces based on SMR drives. An SMR-aware file system, such as F2FS or BTRFS, seems to be a good choice. By this way, we don't need to make any changes with our traditional ITD storage engine. So we evaluate F2FS with our macro benchmark. The test aims to simulate OSS workloads. The x-axis is the test time hours, and the y-axis is the write throughput of a chunk server with 60 drives. We started the test with 4 gigabytes write throughput and filled the drive to 80% space utilization at the first 12 hours, and then trigger random chunk deletions. The black baseline shows that random deletions have little impact on the performance of ext4 on CMR drives. Then we use F2FS to load SMR drives. When random deletions are triggered, F2FS encounters an up to 70% throughput drop. I will introduce 2 observations about the test. The first observation is about OSS workloads. In a typical OSS cluster, a chunk server should serve hundreds of KV servers. Each KV server could open tens of Pangu files for write. We refer to each active Pangu file as a stream and divide them into 3 categories. The OSS data write streams occupies around 13% space on disk and have quite short lifespan. OSS metadata write streams have list data, and the chunks are really small. OSS GC streams have the most data, and most of the chunks can be large. And the number of streams called stream concurrency is usually around 100 per chunk server. All of the three kinds of streams perform random deletions within a period of time. We can see that OSS streams have quite different characteristics on data hotness, chunk size, and data volume. The other observation is about F2FS. Normally, F2FS opens one zone at a time and puts all the chunks from different streams into same zones. When chunk A is deleted, all three zones have garbage space, and that should be reclaimed by F2FS GC. We confirm that by observing the metrics of F2FS. The first y-axis is the dirty segment count of F2FS. The green line shows that after the random deletions are triggered, the dirty segment count continues to grow. And the orange line shows that F2FS GC is frequently triggered. So under the OSS workloads, mixing chunks results in heavy overhead of F2FS GC. That's the reason for the poor performance. So our technical choice is to build a new user space storage engine directly on HM-SMR drives. By co-design with OSS, we expect to achieve high performance on the OSS workloads. Let's move on to our design. Unlike traditional HDD storage engine, SMRSTORE does not rely on any traditional local file systems. It sits in the user space and communicates with SMR drives by zone blocking interfaces. The functionalities we'll talk about today include on-disk layout, data index, and zone management. SMRSTORE follows a log structure design and uses a customized log called record. Record is a basic unit on disk for SMRSTORE's metadata and user data. The record has three parts. The header has a record type, record size, and especially the information about the payload. The payload is in variable size and has extra content that we should write to disk. The padding is for 4 kilobytes alignment because of the direct I/O syscalls. Here is an overview of layout on an SMR drive. We divide the address into 3 partitions. The first zone is the super zone. It records the information about the format, such as timestamp and version. The next 400 zones make up the metadata partition. It stores SMRSTORE's checkpoint and journals. A checkpoint is a copy of all metadata in memory. Inside each meta zone, there are 3 kinds of records. The zone header record has information which helps to identify the zone's validness. And the other 2 types of records are used to store serialized checkpoints or journals. Chunk data is stored in data partition. Inside a data zone, except for the zone header record, there is only one kind of record, data record. Generally, SMRSTORE will create a data record of each write. So the payload of the data record is actually part of the chunk. The format of the payload is quite different from other types of records. We further split the payload into multiple slices. Each slice has 4 kilobytes user data and 32 bytes footer. The design aims to reduce read amplification when we just need to read a small part of the payload. So with such a layout, how does SMRSTORE organize in-memory structure effectively and optimize data placement to reduce the overhead of garbage collection? Our design about data index is quite straightforward. Suppose that we have such a chunk on disk. It has 4 data records that are distributed among 2 data zones. In memory, there is metadata for the chunk. SMRSTORE has a new structure called index group list. The list has a series of index groups. Each of them corresponds to only one data zone. The record index has the logical location in the trunk and the physical location in the data zone. That's exactly how we implement the logical to physical mapping. By maintaining all the record indexes in memory, we have all the locations of the chunk data. We designed 3 workload-aware data placement strategies to reduce the overhead of garbage collection. First, we separate chunks into different zones by their stream types and adapt their most chunk size limit for a data zone. We also try to allocate an empty zone by round-robin allocation in the zone pools. The left figure shows the F2FS-like data placement that all chunks are interleaved in same zones. SMRSTORE prepares 3 pools to separate the different streams on disk. And we'll try to look for a new empty zone for chunk B to separate from chunk A. We also set the chunk size to a zone size. By this way, we try to fill a data zone by only 1 chunk. When chunk A is deleted at a time, SMRSTORE can reset and reuse zone 1 directly. We also observe that some chunks could be smaller, so they should be interleaved with the other chunks. So SMRSTORE GC is still inevitable, but the first 2 pools can cover up to 78% traffic, so the amount of GC has been much reduced. We evaluate SMRSTORE with our benchmarks and also have a study on the effectiveness of the placement strategies. The storage servers have 7 configurations except the drives. The CMR and SMR drives they use have similar raw performances. In the micro benchmark, the x-axis has different out sizes, and the y-axis is the write throughput of a single storage engine. The black baseline is the throughput of an X4-based storage engine on a CMR drive. We observe that SMRSTORE performs not well with small out sizes. That's because SMRSTORE always tries to allocate different zones for different chunks. So the right head of the disk has more jumpings between zones. In fact, that's OK for us because most OS writes are in large out sizes. SMRSTORE can provide a comparable write throughput with about 64 kilobytes out sizes, and can even provide 30% higher throughput with 1 megabyte out size. This figure about macro benchmark has been shown before to study the F2FS. We run the test with SMRSTORE. The origin line shows that SMRSTORE can deliver consistent write throughput and perform 2.16 times faster than F2FS. In order to study the effectiveness of SMRSTORE placement, we compare the performance of SMRSTORE between enabling and disabling the strategies. The black line shows SMRSTORE suffers a similar performance drop with F2FS if we disable the strategies. And the orange line performs better with optimized placement. The CDFs of zone utilization in the right figure demonstrate that the performance improvement benefits from a better desk placement that most zones are either empty or full. By enabling all 3 strategies, SMRSTORE can achieve 2.35 times higher throughput. We built a new user space engine, SMRSTORE, and designed 3 workload-aware data placement strategies according to the characteristics of OSS workloads. And SMRSTORE can deliver comparable performance with the Active4 on CMR drives. And on the OSS workloads, SMRSTORE can perform much better than F2FS. By deploying SMR drives, OSS can decrease the total cost by around 15%. That's all of my presentation today. Thanks for listening. Please feel free for any questions.